So for the first contributed talk of the workshop, we have Jam Kabeer Ali Khan. He's going to talk about estimating quantum-proof classical programs.
All right, cool. Hello, everyone. Good morning. So I'm Jam. So I'm Jam, and this is joint work in collaboration with Anurudh, Peduri, Gilles, Barthe, who is in the audience, and Michael Walter. So I'll be presenting Traq, estimating quantum cost of classical programs. So we all know that many quantum algorithms do have advantage over the classical ones, and some example would be Grover's and the Shor's. And actually there's a long list of algorithms being tracked upon in the website called Quantum Algorithm Zoo, if you want to look it up. But then the question is, how do we leverage these existing how do we leverage these speedups in existing classical programs, right? We already have a lot of classical programs. How do we show that, okay, maybe at few part we can get that advantage from some of the quantum algorithms? So one of the ways to do so is quantization. And in this context, quantization could be kind of seen through this diagram. I'll explain. So let's say we have a classical program with subroutines. And these subroutines are performing some computational task. It could be searching, for example. And we apply quantization on this classical program with subroutines, and it transforms into a quantum program. And this quantum program and the original classical program are doing basically the same thing up to an extent. But then what do we how do we exactly concretely achieve this quantization? One of the ways to do is compilation. So you compile the original source classical program into a quantum program, and you get a resulting quantum program that does the same thing, but with a better algorithm that gives you some level of speed up. Okay, but then the question is, how do we estimate the advantage, right? Okay, we have a resulting quantum program that does this computational task with a different algorithm, but it's still, how do we know that this one is better than what we had originally? There are multiple ways to do so. We can execute it. We have the resulting quantum program. We can go run it on a quantum computer. But then, of course, quantum computers are not widely available yet, and it also tends to be more expensive. We can simulate, of course, and the simulation is also costly. It does not scale after a certain number of qubits. We can do manual analysis. A lot of people do this. They do this theoretical analysis of the cost. And of course, you have to do a lot of bookkeeping. Then it easily becomes tedious and error prone. So we are trying to find a fine balance between these approaches. We are trying to see if we can get something better. So in this work, the research goal is that we want a formal and practical framework to automatically estimate the quantum cost of classical programs. In summary, basically, we want to see how do we automate while maintaining some of the formal guarantees, this process. It has to be automated, as I said, so no manual cost analysis, no manual bookkeeping, ideally. It has to have formal guarantees, and also it has to be accessible to few people. So if you are a classical programmer, you just want to see if you can benefit from a quantum algorithm, you don't need to go learn all the quantum computing and do so. So let's see how do we do this. In this work, I will present Traq, which is the framework to do so. The way we do it is we introduce a classical probabilistic source language called CPL. We enable quantization that I mentioned before via compilation, and the compilation goes to an actual quantum programming language. And then, based upon this compilation, we extract sort of a cost model. So there's multiple cost functions in this cost model, and we do this to kind of like estimate the cost at the source level. So you don't really need compilation once you have this and it's on. And of course, we give provable guarantees both for compilation and cost, as we'll see. So let's look at a simple example to demonstrate this process. So let's say it's a very basic example. We have a list, and we just want to find if there's a one or not. On the left-hand side, you have the program, which just simply performs mainly a search. And the search in this language is a primitive. So intuitively, we know that search is search, right? It could be implemented either classically with a linear search, or it could be very well a Grover's algorithm in the back. So Traq, the basic idea would be that the search primitive could have a classical compilation, but also a quantum compilation. The quantum compilation will go to a Grover's algorithm, and then you will have, ideally, a resulting quadratic speedup over the similar classical search. But there's more problems to it, as you will see. Let's take the previous example, make it a bit more interesting. Instead of a row, we are just searching over a matrix. In this matrix, we try to find a row with all ones. And here, what you will see is that now we have a nested search going on. We not only search on the outer rows, but we also search within the row to see if they're all ones or not. So as I mentioned, the search in this case would go to Grover's algorithm. Well, Grover's algorithm has certain constraints, right? The predicate should be unitary. Predicate in this case is this is_row_ones function. What it means is now we have to define a unitary compilation for the language as well. What it means to be unitary in the most basic sense is the resulting oracle or the program should be reversible. There's a more mathematical definition, but without getting into much detail, that's the most basic sense. So Traq does this. Traq not only defines the general quantum compilation, but also takes care of this compilation which is unitary so that the programs that you end up with are reversible. But then still the story of compilation is not over. There's more interesting problem as well of taking care of the errors. Most of the times when you write the classical algorithm, we don't need to worry about the fact that they can fail. Sometimes you will get a result that does not make sense, but well, quantum algorithms do. They have a failure probability. So how do we take care of this to make sure the resulting quantum program has a certain error, and it's not just errors that you don't know about. You have chosen the resulting quantum program to have a maximum error. So the way we do this, we take the source level code, we perform automated error annotation because, as I said, primitives are the one being compiled to a quantum algorithm. So the source of errors tend to be the primitives themselves, right? We annotate with epsilon1, epsilon2 in this case, for example. We run an error analysis. This error analysis is going to give you a expression which could be treated as a constraint, sort of. This error equation could be sent to a solver, or you could have some basic strategies to get the epsilon1 and epsilon2 values that satisfy this constraint. Once you have this, you can perform the compilation. Now the best part about this is that once you have solved this, you kind of know what the resulting program, how much error it's going to have, and you will get those guarantees. Okay, so this is the error analysis. So this is the compilation story in a sense, but then we also want to make sure that this is correct, right? What we are doing is correct, and we have to define the compiler correctness. And in this case, we do. I'm just going to show the general quantum compiler correctness in this case. So what we do is we give semantics to both the source and target, and reason about the distance, the TV distance between the resulting distributions from the semantics. Why we will do so is because the semantics for both languages are probabilistic, and we show that the semantics of both the source and the target are gonna be error close. So the error that you were comfortable with having in your program, that's the utmost deviation that these two semantics are gonna have. This is the notion of compiler correctness in our case. And then we also have unitary compiler correctness, because I mentioned there is unitary compilation as well. That would be in the full paper, not in this talk. But then, as I said, the original idea was allowing estimation of quantum cost, right? I have defined the compilation, but going back to the cost analysis, how do we do this? Before I get into the exact cost analysis, let's make sure we are on the same page about the model, the cost model that we choose. In this case, we choose query model, which is in the basic sense is counting the number of queries made to a function f. Why do we use this? It's sort of a well-established proxy for a lot of other models, time complexity being one. Also widely used in theoretical quantum computing literature. So precisely when we say a classical query is just a call to a function f. Inner setting, a quantum query is actually invoking a unitary UF, or its inverse. And exactly what it means to be UF in this case is defined by this statement. Okay, so now we know the cost model. What are the cost functions that we can get out of it? In this work, we have three. We have the havoc cost, input dependent cost, and unitary cost. The first two I will get into more details. So havoc cost. What does it mean to have havoc cost? Essentially, when we say about it's a sort of a worst case cost in the presence of errors. So what does it mean? So usually when we have a notion of worst case cost, we say, okay, our program is doing what it was supposed to, and here's the worst case cost. But in this case, there's errors, right? In those failure probability of the algorithm, it could do something that you cannot easily reason about. But it is still program execution. So not only we are taking into account the intended behavior, but also the chances that this program fails, and given all that, what is the worst case cost? That would be havoc cost. So let's look at how it works. We have the left-hand side, we have the program, and based on the structure of the program, we apply a cost function. And the cost function is just a havoc queue, and it's going to run and give you a cost expression. Some of the details are hidden because of complexity, but that's the notion of idea. That's the idea. Okay. Then we also support input-dependent expected cost analysis, and the motivation in this case is that we want to estimate the advantage given a specific input. Why do we do this? It's because a lot of these quantum algorithms tend to have a better expected cost over their worst case cost. So in this case of root n over k for growers, if you know the number of solutions, which is k, which is better than the worst case, which is just over root n. Similar to havoc cost, this also works structurally on the syntax of the program. And you run the cost function and you will get a cost equation. Again, some of the details are hidden for this talk. Yeah, so this is expected cost. And now let's look at the overview. There's a lot of equations going on. Let's look at the big picture of this whole theoretical setting, right? We defined a probabilistic classical language. We gave it a compilation to a quantum language. We have the compiler correctness for it. Based on that compilation, we defined some cost functions. Now you will see in the full paper, we have the cost correctness as well. The cost functions I just showed you, they are sound. Best part is once you know that this is all sound, you don't really need compilation, right? Your cost function could just run on the source level. And I think so this is the essence of this framework, that you can kind of take that quantum cost analysis where you need to worry about the quantum stuff, you can just bring it to the classical setting at the source level. Okay, there's a few more interesting things that we do. We have Traq implemented as a Haskell package. So the total implementation brings up to 9,000 lines of code, and we do some interesting choices in the architecture, one of them being that the AST is polymorphic over the set of primitives. What does it mean is that if you want to add a new primitive, you don't need to go changing the AST, which will lead itself to an expression problem, going through the whole 9,000 lines of code, changing everything. You just need to implement a primitive and pass it to the original AST, and you will get a new primitive. So it's, in a sense, it is more extensible because of this. And then another feature that we use for Haskell is we enable adding new primitives via type classes. So as I said, again, to add new primitive, you don't need to change the original structure of the code. There's a bunch of type classes. In this case, for example, one type class would be expected cost. You introduce a syntax, you implement those type classes, and the primitive gets added. Basically, if you want to support more quantum algorithms, this is one way to do so. So what are the primitives we support so far? We have the annual search. Some of these we already seen. We have the amplitude amplification as well. And we have the Simon's algorithm, which is very useful for cryptanalysis attacks. And we have min, max, argument, argmax. So these are the primitives that we support as of now. But of course, there can be more that could be added. Some of the case studies we do to show the applications of Traq are related to cryptanalysis. The most interesting ones being two is the 3-round Feistel attack and Ibn Mansur. So yes, so these are the cryptanalysis case studies we do. These are taken from literature. Then we have optimization as well. We have the max case set and we have 0-1 knapsack. So without getting details, the best part is this is existing in the current literature, right? You're taking problems from the papers that have already published. So we are trying to capture that in a framework to an extent. Okay, then to conclude, the list of contributions in this project include a classical probabilistic source language to express these programs. And then you have a compilation from this probabilistic source to a quantum language. As I mentioned, there's a few challenges we address to do so. Then based upon that, we have cost analysis for the source programs to estimate quantum advantage. So basically, as I said, you don't need to compile. If this is sound, you can use this cost analysis at the source level, which is just write a classical program, get an idea whether it's going to benefit you or not to use a quantum algorithm. And then this all has to be guaranteed, right? This has to be correct. So we have the formal guarantees and a lot of theorems proved to do so on compilation and cost both. And as I mentioned before, we use some level of error analysis introduced. So those guarantees are based upon the error analysis. And then we have a Haskell package. The future directions for this work would include supporting more ghost models, right? The query model is good enough for certain purposes. Actually, it's a very good target for the start of the work. But then we might want to introduce gate complexity so we can get a better idea of how the hardware implementation works. And we can also enable support for more efficient quantum algorithms. There's, for example, a class of quantum algorithms called variable time quantum algorithms, and that would allow even better advantages for some cases. Yes, so this is the QR code to the archive and the QR code to the GitHub, and that's all talk. Thanks to you all for listening.
Thank you for the really cool talk. I really like how CPL gives you this extensible set of primitives where you can actually plug in whatever predicates you want. My question is, which classical primitives do you think would be the hardest to implement into the system? Like, you can imagine if your classical program does some really weird control flow or memory or I/O, that might be pretty hard to compile to a unitary.
Yes, indeed, this is the case. So this leads itself to quite a couple of challenges that would not be addressed as the current work, right? So for example, I/O. We have not explored exactly how this would work out, but for example, we did explore adding, for example, boundary recursion or things to the source level language. So as a unitary compilation requires some level of constraints. We have to kind of deal with those and live within those constraints, right? For boundary recursion, we enable and a few extensions, for example, lists in the main syntax of this. So the full paper, if you look it up, it has more features, including lists and some basic conditionals and boundary recursion as well in the code. But to add more features that are more complicated control for it will require some more exploration. I don't really have a better idea at that point. Yeah.
Thank you. With respect to the primitives, Grove and search, that gives you quadratic speedup on a quantum computer. Do you have, I missed that, do you have anything that also makes it possible to express quantum Fourier transform? Most programs that have any speedup, exponential speedup at all, seem to factor through quantum Fourier transform. So
Yep.
do you generate any of those programs?
So this is one of the interesting work we were looking into. So for example, having a primitive like Shor's or a quantum Fourier transform would be an interesting thing. For this, so far, we have added these primitives as of now. The interesting one being the general amplitude amplification and the Simons, and of course the search is kind of part of it. But yes, that would be definitely an interesting direction to explore, because that requires some level of changes in not only the compiler, that one needs to be careful of how they work out with the other primitives, the existing ones. So that's kind of an interesting problem.
Thank you for the talk. How about compositionality? Namely, for instance, if I have a search function that itself uses a search function.
All right, that is my first example indeed. Maybe that's going to be a long way. Okay, there we go. So this is actually quite an interesting case, right? This search is using a predicate that itself uses search, in a sense. This all is kind of a search. It's just the semantics are going to be different. But they are still using the underlying is Grover's algorithm. The compositionality is indeed crucial, so we do make sure that their theorems are compositional in the sense that as long as your primitives satisfy a promise, and you are kind of taking care of the constraints that are required for the compilation, this all theorems kind of compose. So we have a notion of functional spec. And in the case of the implementation, we also take care of type classes. So you just need to add it, and it kind of works into the system already. But in the theory, there is the notion of functional spec to prove those theorems instead of just relying on one specific primitive at a time.
Very cool, thanks.
Okay, thank you.